Hello, my name is Neil Coles, and this is my Physics 2212 Circuits Lab Report. Introduction. The purpose of this lab was to use multimeters to measure actual values of conventional current and potential differences in circuits. We also observed the behavior of ohmic resistors and capacitors. Equations used in this lab were Ohm's law, which is V equals I times R, which is volts equals current times resistance. The loop rule, which is you just add up all of the potential differences across the points and it equals 0. And the node rule, which is current 1 plus current 2 equals current total. And a little preview of our results, the node rule and the loop rule both held to be true, and the current in the RC circuit is time dependent. Some of the models of this experiment, down here you can see kind of the setup. We got resistor 1, resistor 2, and the battery. Loops going this way with current going this way. The system is the battery and the resistor circuit. And the surroundings is everything else. Here we can see a little bit of a graph of the node rule, which is all the currents in have to equal all the currents out, or all the currents in minus all the currents out equals 0. And we were getting an initial reading of 19.7 milliamps. In experiment 1, for the calculations, experiment 1, we connected two multimeters to two different resistors and two different 1.5 volt batteries. We calculated this using Ohm's law to find the voltage, because the voltage equals the current times resistance. Since we had two 1.5 volt batteries in series, it equaled 3, and we had a 47 ohm resistor and a 100 ohm resistor, and you can just add them up since they are in series, and then it equals 147 ohms. So then 3 divided by 147 is 0.0204 amps, or just 20.4 milliamps. And then we also calculated the potential difference between the points. And from point C to point D, which was the points right before and right after the 47 ohm resistor, we got negative 0.9 volts. And from E to F, which is right before and right after the 100 ohm resistor, we got negative 2 volts. In experiment 2, we charged the capacitor. We connected the battery to the capacitor, and it took 7 minutes and 7 seconds to charge, and 5 minutes and 18 seconds to discharge. Possible sources of error in this experiment. We could have had a faulty ammeter or voltmeter. We could have set up the circuit incorrectly. There could have been human error with the stopwatch, and some of the equipment may have been faulty or not perfect. And also, our group had a major problem finding working multimeters, so we eventually had to join another group that had working ones. We believe the fuses were blown by the students that didn't know how to use the equipment, but we have no way of telling for sure. What if question? If you charged a capacitor with no resistor in the circuit, how quickly would our ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? Explain. Use the ammeter to measure how long it would take to charge the capacitor when you connect it directly to the battery in the ammeter. Discuss why the measured time is different from the predicted time. The capacitor would have charged faster since there was no to little resistance, meaning that it would have charged and discharged almost immediately. But we have no way of comparing the actual results to the hypothetical. And a conclusion to this lab report, the experiment proves that the node rule and loop rules were both accurate, theoretically.